Let us now look at the decision tree model, a popular method used for classification. By the end of this video, you should be able to explain how a decision tree is used for classification, describe the process of constructing a decision tree for classification, and interpret how a decision tree comes up with a classification decision. The idea behind decision trees for classification is to split the data into subsets where each subset belongs to only one class. This is accomplished by dividing the input space into pure regions, that is, regions with samples from only one class. With real data, completely pure subsets may not be possible, so the goal is to divide the data into subsets that are as pure as possible. That is, each subset contains as many samples as possible of a single class. Graphically, this is equivalent to dividing the input space into regions that are as pure as possible. Boundaries separating these regions are called decision boundaries, and the decision tree model makes classification decisions based on these decision boundaries. A decision tree is a hierarchical structure with nodes and directed edges. The node at the top is called a root node. The nodes at the bottom are called leaf nodes. Nodes that are neither the root node or the leaf node are called internal nodes. The root and internal nodes have test conditions. Each leaf node has a class label associated with it. A classification decision is made by traversing the decision tree starting with the root node. At each node, the answer to the test condition determines which branch to traverse to. When a leaf node is reached, the category at the leaf node determines the classification decision. The depth of a node is the number of edges from the root node to that node. The depth of the root node is 0. The depth of a decision tree is the number of edges in the longest path from the root node to the leaf node. The size of a decision tree is the number of nodes in the tree. This is an example of a decision tree, and it can be used to classify an animal as a mammal or not a mammal. According to this decision tree, if an animal is warm-blooded, gives live birth, and has a vertebrate, then it is a mammal. If an animal does not have any of these three characteristics, then it's not a mammal. A decision tree is built by starting with all samples at a single node, the root node, and adding additional nodes when the data is split into subsets. At a high level, constructing a decision tree consists of the following steps. Start with all samples at a node. Partition the samples into subsets based on the input variables. Here, the goal is to create subsets of records that are purest. That is, each subset contains as many samples as possible belonging to just one class. Another way to say this is that the subsets should be homogeneous or as pure as possible. Repeatedly partition data into successively purer subsets until stopping criteria are satisfied. And an algorithm for constructing a decision tree model is referred to as induction algorithm. So you may hear the term tree induction used to describe the process of building a decision tree. Note that at each split, the induction algorithm only considers the best way to split the particular portion of the data. This is referred to as a greedy approach. Greedy algorithms solve a subset of the problem at a time and is a necessary approach when solving the entire problem is not feasible. And by feasible, I mean computable in a reasonable amount of time or space. Using a greedy algorithm is necessary for decision trees. It is not feasible to determine the best tree given a dataset, so the tree has to be built in a piecemeal fashion by determining the best way to split the current node at each step and combining these decisions together to form a final decision tree. In constructing a decision tree, how is the data partitioned? How does a decision tree determine the best way to split the set of samples at a node? Again, the goal is to partition the data at the node into subsets that are as pure as possible. In this example, the partition shown on the right results in more homogeneous subsets since these subsets contain more samples belonging to a single class than the resulting subsets shown on the left. So the partition on the right results in purer subsets and is the preferred partition. Therefore, we need a way to measure the purity of a split in order to compare different ways to partition a set of data. It turns out that it works better mathematically if we measure the impurity rather than the purity of a split. So, the impurity measure of a node specifies how mixed the resulting subsets are. Since we want the resulting subsets to have homogeneous class labels, not mixed class labels, we want the split that minimizes the impurity measure. A common impurity measure used for determining the best split is called the Gini index. The lower the Gini index, the higher the purity of the split. So the decision tree will select the split that minimizes the Gini index. Besides the Gini index, other impurity measures include entropy or information gain and misclassification rate. The other factor in determining the best way to partition a node is which variable to split on. The decision tree will test all variables to determine the best way to split a node using a purity measure such as the Gini index to compare the various possibilities. Recall that the tree induction algorithm repeatedly splits nodes to get more and more homogeneous datasets. So when does this process stop building subsets? When does the algorithm stop growing the tree? There are several criteria that can be used to determine when a node should no longer be split into subsets. The induction algorithm can stop expanding a node when all samples in the node have the same class label. This means that this set of data is as pure as possible, and further splitting will not result in any better partition of the data. And since getting completely pure subsets is difficult to achieving with real data, this stopping criterion can be modified to when a certain percentage of the samples in the node, say 90% for example, have the same class labels. The algorithm can stop expanding a node when the number of samples in the node falls below a certain minimum value. At this point, the number of samples is too small to make a much difference in the classification results with further splitting. The induction algorithm can also stop expanding a node when the improvement in impurity measure is too small to make much of a difference in classification results. Additionally, the tree or the algorithm can stop expanding a node when the maximum tree depth is reached. This is to control the complexity of the resulting tree. There can be other criteria that can be used to determine when tree induction should stop, but we'll stop here. Let's take a look at an example to illustrate the induction process. Let's say we want to classify loan applicants as being likely to repay a loan or not likely to repay a loan based on their income and amount of debt they have. Building a decision tree for this classification problem could proceed as follows. Consider the input space of this problem as shown in the left figure. One way to split this dataset into more homogeneous subsets is to consider the decision boundary where income is T1. To the right of this decision boundary are mostly red samples, and to the left are mostly blue samples. The subsets are not completely homogeneous, but that is the best way to split the original dataset based on the variable income. The decision tree boundary is represented in the decision tree by the condition income is greater than T1 at the root node. This is the condition used to split the original dataset. Samples with income greater than the threshold value of T1 are placed in the right subset, and samples with income less than or equal to T1 are placed in the left subset, just as shown in the left diagram. Because the right subset is almost perfectly predicts that lenders will repay properly, the right subset is now labeled as red, meaning that the loan applicant is likely to repay the loan. The second step, then, is to determine how to split the region outlined in red. As shown in the left diagram in input space, the best way to split this data is specified by the second decision boundary with depth equals T2. This is represented in the decision tree on the right with the addition of the node with condition depth greater than T2. Samples with a value for depth greater than T2 are shown in the region above the decision boundary. This region contains all blue samples, and so the corresponding node is labeled blue, meaning that the loan applicant is not likely to repay the loan. The third and final split looks at how to split the region outlined in red in the left diagram. The best split is specified by the boundary with income equals T3. This splits the red region into two pure subsets. The split is represented in the decision tree by adding a node with condition income is greater than T3, and the left resulting node is labeled blue and the right resulting node is labeled red, corresponding to the resulting subsets with the red border in the left diagram. We end with the final decision tree on the right, which implements the decision boundaries shown as dashed lines in the left diagram. These decision boundaries partition the dataset as shown. The label for each region is determined by the label of the majority of the samples. These labels are reflected in the leaf nodes of the decision tree shown on the right. You may have noticed that the decision boundaries of a decision tree are parallel to the axes formed by the variables. This is referred to as being a rectilinear. The boundaries are rectilinear because each split considers only a single variable. There are variants of the tree induction algorithm that consider more than one attribute when splitting a value. However, each split has to consider all combinations of combined variables, and so such induction algorithms are more computationally intensive, or we can also call them more computationally expensive. There are a few important things to note about the decision tree classifier. The resulting tree is often simple to understand and interpret, and this is one of the biggest advantages of decision trees for classification. It is often possible to look at the resulting tree to see which variables are important to the classification problem and understand how the classification is performed. For this reason, many people will start out with a decision tree classifier to get a feel for the classification problem, even if they end up using a more sophisticated model later on. The tree induction algorithm, as described in this lesson, is relatively computationally inexpensive, so training a decision tree for classification can be relatively fast. The greedy approach used by the tree induction algorithm determines the best way to split the proportion of the data at a node, but does not guarantee the best solution overall for the entire dataset. Decision boundaries are rectilinear, and this can limit the expressiveness of the resulting model, which means it may not be able to solve complicated classification problems that require more complex decisions or decision boundaries to be formed. In summary, the decision tree classifier uses a tree-like structure to specify a series of conditions that are tested to determine the class label for a sample. The decision tree is constructed by repeatedly splitting the data and partitioning the data into successively more homogeneous subsets. The resulting tree can often be easy to interpret. So now let's look at our notebook to do a decision tree classification on our weather dataset in Python.